Alright, welcome to this video. We're gonna go through a question in calculus, quite a useful one I think, and it's from paper 1, 2008, question 7. Right, so let's have a look at it. Here it is. The question gives us an initial statement here where they give us a clue. They say that the integral from 1 to 5 of 3 times some function, which is kind of a mystery function. They don't tell us what it is. They tell us that the value of that integral, definite integral because it's got limits, is 12. And then using that clue, they ask us to show that this is also true. And then they ask us to find the value of this longer thing down here. So let's look at it in parts. In the first part, I just want you to notice before we start that the limits here are from 1 to 5. But here the limits are from 5 to 1. So they're flipping the limits around. You might already know what that does to the answer of one compared to the other. The other difference that there is between these two is that this has a 3 and this one doesn't. So they're gonna test whether we know two relationships about integrals. And let's have a look at what those relationships are. First one we need to know is this, well, let me first write what they give us. They give us that the integral from 1 to 5 of 3 times some function with respect to x is equal to 12. That's one clue that they give us. And they ask us to show that the integral from 5 to 1 of just the function itself without the 3 with respect to x again is equal to minus 4. I think that's what we're given. There it is, minus 4. Okay. Now, what things are they testing here? Well, one of them is the relationship between an integral when it's multiplied by a number and the integral when it's not multiplied by the number. So what happens there? What happens to numbers or constants with integrals? So the relationship there to learn, which I believe you have in your formula book, but anyway, you should definitely know it so you can use it, is this one, that any integral of a constant times a function dx is the same as taking out the constant, putting it in front, in this case it would be the 3, and doing the same thing. These two are equivalent. In other words, the integral you can take, the constant you can take it out. An example is this: if I have the integral of 3x, the integral of 5x to the power of 2 dx, well, the power goes up to the 3, as you know, and then I've got to kind of differentiate this and see what I would get. I would get 3x squared, but I don't want 3x squared, I want 5x squared. So I need a 5 at the top here and a 3 at the bottom, so that when the 3 comes down, it cancels with this 3 and I get 5x to the power of 2. So this is true, that these two are equal. What about this one? If I take out the constant, then the integral of this is just x cubed over 3, right? And this 5 comes at the end and multiplies at the end times the value of that integral, and I get 5x cubed over 3. It just multiplies on the top of the fraction, remember, so I get the same answer in both cases. Okay, so that's just one example, but it's true that when you take an integral of a function multiplied by a constant, or you multiply the constant times the integral afterwards, you get the same answer. So that's one relationship that they're testing that you know. The second one that we need to know here is this one. What happens if you flip the limits from 1 to 5 or from 5 to 1? And what happens there is that the integral from a to b of any function with respect to x is equal to the negative of the integral from b to a of the same function. These two are the two things that they're testing whether we know. They're not very complicated things. Basically the sign changes if we swap the limits, and here the constants you can always take it out, but remember it's only if it's a constant. You can't take out, if you have xf of x, you can't take out the x outside because that's not a constant, that's a variable. Right, good. Now with those two tools we should be able to solve the question. Let's see, we take the original that they give us, which is this one over here, right? The question actually gives us that, it's here. We take that which they give us and we say, well, if the integral from 1 to 5 of 3 f of x dx is equal to 12, that implies that, well, we can just say that this is equal to 3 times the integral of 1 to 5 from 1 to 5 of f of x dx. All I've done is to take in the 3 outside. All of these are equal in maths, so we can just divide by 3 both sides of the equation, right? Here and there we can divide by 3 and we get that 4 is equal to the integral from 1 to 5 of f of x dx. And so we're nearly there, because they want us to prove that from 5 to 1 is equal to minus 4, and we've got that from 1 to 5 it's equal to 4. So all we have to say now is that using this relationship here, which always in maths is nice if you can label it, so I'm gonna call this relationship number 2, and you can always call this one over here number 1, even though we haven't alluded there, but we could say here from 1. And now we can say from 2. We can say, well, from 2 I know that the integral of f of x from 1 to 5 dx is equal to the negative integral of 5 to 1 f of x dx. Negative. And therefore we should just show this. Therefore the integral from, let's change colors back to white again because this original thing is in white, so now we can say that that's true. Therefore these 3 dots like this mean therefore we can say that the integral from 5 to 1 of f of x dx must be equal to minus 4. Since this one here is equal to 4 and we just made this relationship here, we can say that it's equal to minus 4. Okay, that is quite a lot of work for 2 marks, but don't worry about that, because as you practice these you can do them more and more quickly, and I've done it in quite a long-winded way to explain it all, but you can use these 2 relationships here and then just pretty much say that well, you can say this here and well, yeah, you can jump a couple of lines there, but I've just laid it out all so that you can see it properly. Hopefully you can see what happened there, and all of that is for 2 marks, which is not so much, but what matters here is revision, and this should be handy for you to learn. You can use those relationships loads of times. They're really, really useful. Okay, I didn't really label here what we're doing. This is part A. Okay, so let's have a look at part B, just a little bit that's similar in terms of convoluted, really. But they're testing if you know a separate thing. So let me see. Alright, part B. B, find the value of this. This looks really convoluted, but you'll see that it becomes not so hard in a second. So let's look at this closely first. We've got the integral from 1 to 2, and then the integral from 2 to 5. So it's really a continuous from 1 to 2 and then from 2 to 5. And then it's a continuous because this object is the same as this object. So hopefully you can see that if I have an integral, it's not a very straight line. If I have the integral of a function that I don't know what it is, and I take it from 1 to 2, and then all the way to 5, from 2 to 5, that area is going to be the same as if I just take it from 1 to 5 directly. In other words, I can combine both the integrals that I've just been given into one same integral, and that's going to allow me to solve the question a lot better than if I keep them separate. So let's see. So really here they're using this other property of integrals, which is the integral of a to b, from a to b of f of x, is to say, well, let's use here, let's use c. From a to c is the same as the integral from a to b plus the integral from b to c, right? That's what we're using. From a to c, you can chop it up in two parts, and if you add them, you're going to get the same answer. So this is the new, the other relationship that they want us to use with integrals, and they're testing us here to see if we really understand what it means. I deleted too much. Okay, let me see. So let's write it down. From 1 to 2 of x plus f of x. So we need to find the value of the integral from 1 to 2 of f of x plus x dx plus the integral from 2 to 5 of f of x plus x dx. These two are the same object, so we can say, we can find that, and we can say that all of that equals, we can say that all of this equals the integral that I'm interested in. I could just call it I. And then I can say also I equals the integral from 1 to 5 directly of f of x plus x, all of this dx. Okay, that's got to be true. Now if we look at the original question, it says here that this guy is equal to 12. We know that from 1 to 5. And now we're looking at the integral from 1 to 5, right? But the question doesn't give us f of x plus x. The question gives us f of x. There's a 3 here, but you can divide by 3 both sides because you can take it outside, really, if we use the relationship from before, right? This has somehow been rotated a little bit. That's better. So we know from the other question that we had that the integral of f of x dx is equal to 4 from 1 to 5. Right, we had it from before. It was really equal to 12 when you had a 3 here, but then if you divide by 3 both sides, it becomes equal to 4. So we know this much. You can state this in your question that you know that, right? Now, given this, then you can start fiddling around with this, because this integral right here, you can split it up into 2 parts, but instead of splitting it up into units, into limits, like we joined the limits here, what we're going to split it up is into this and that. Okay, and here's a fourth relationship. Really, we're using everything in this question. This is why it's so good to practice it. If you can solve this one, you're really in a good position to solve many others. This integral here can be split up into 2. So it equals from 1 to 5 of f of x dx plus another integral from 1 to 5 of x dx. So all I've done is this one goes over here, and this one goes over here. All I've done is to split that up into 2. Okay. Now this guy is just 4, and that's him. So I've already got the answer to that, and even if I don't know the function, I don't have to integrate it, because I know that it's equal to 4. So all of this here is equal to 4. That's perfect. Saves me a lot of thinking, and the only challenge left is this guy, and hopefully you can do him easily, because this is just the integral of x. The integral of x is super simple to do. It's just x squared over 2, and you need to put the limits in, which are from 1 to 5. So then you're left with a very easy problem to solve. You put the first limit in there, and then the second one, and you subtract them, right? So x squared, you put the 5 in here, that's 25 over 2, and then you subtract from it the 1, the limit of the 1 in there, which is 1 squared over 2. Since they're both over 2, you can subtract them. 25 minus 1 is 24. 24 over 2 is 12. 4 plus 12 is 16. Since we're talking about areas under graphs, right, all of these are areas, you have to speak of units squared, because they haven't given you any other units on the question. Okay, so this is your integral that they're asking you for, I, and that's the end of the question. This is for 5 marks. Now, those two questions, A and B, are really useful, and I recommend that you work them out on a piece of paper on your own. After seeing this video maybe 1 or 2 times, you can play it backwards and press play if you get stuck, but really try to look at the relationships that I've used, which have to do with swapping of the limits from A to B. What happens when you go from that to B to A? Basically, you just put a minus in front. The other relationship that we used was that if you have a constant inside of the integral, you can just put it outside. It's exactly the same as putting it here, right? Then we saw that, oh, sorry about that. Then we saw that if you have the limits from A to C, or originally actually we did it the other way around, we had from A to B of some function plus from B to C of another function. I'm taking away the dx's for speed. It's the same thing as doing the integral from A directly to C of the same function, right? From A to B, B to C, it's the same as doing from A to C. That's the third relationship that we used. And the fourth one was that if you have, God, it's going crazy. A ver. The fourth one was that if you have an integral, some function plus another function, in this case this function was very simple and it was just an x, but this works with any function. If you have the integral of the sum of 2 functions, dx, that's exactly the same thing as saying this. Right, splitting it in 2. And again, I'm taking away the dx's for speed. And those are all the relationships that we used. Using all of that and the original information that they gave you, which was this, you could solve that question. Okay, hopefully that's useful for revision. See you in the next video.